Alright, greetings Mr. Kolazar's class. Today we're going to start talking about electrons. And the focus of our chapter 5 is on the electron. It's really the part of the atom that does, I guess you could say, all of the work. And so what we're going to look at today, a couple of our objectives. First off, the parts of the wave. And then part 2, describe the frequency and the wavelength and how they're related. And then we're also going to do some calculations with frequency and wavelength. So in the past chapter we talked about Dalton's atomic theory, matter composed of extremely small particles called atoms. Atoms are indivisible and indestructible. Atoms of a given element are identical in size and mass and chemical properties, and different atoms combine in simple whole number ratios to form compounds. He'd also talked about Dalton's theory. In a chemical reaction, atoms separate, combined, or rearrange, so we never lose any atoms. And atoms of specific element are different from other elements. Now Dalton had a few incorrections, things he didn't have right. Remember, they are divisible, they are destructible, and their masses or isotopes can be different. Now from Dalton, J.J. Thomson gave us the idea of they have electron, part of the atom with negative charge and very little mass. And then Rutherford's model gave us the idea that the atom is mostly empty space. Remember, we compared the size of a marble to basically the size of the Fargo Dome and Fargo Dome parking lot is where the electrons are versus the marble being the mass of the nucleus. So the proton, neutrons in the nucleus, fast-moving electrons on the outside. However, number 2 in the notes, I didn't explain how the electrons are arranged, and it didn't show why the electrons are not pulled into the positively centered nucleus, and he did not explain that there are differences in chemical properties and behaviors among elements, but these properties repeat every so often, and then as you go further along, those chemical properties continue to repeat or have similar trends and properties. And so we're going to be examining all of those throughout this chapter 5, focusing on the electron. Now, as we're going, this chapter really focuses on the idea that the atom's arrangement came from research involving matter and its interaction with light. So as we look at the interaction of light, light is part of our electromagnetic radiation. Electromagnetic radiation, form of energy that travels like a wave through space. Now, unlike sound, which is also a wave, sound needs medium like air to travel through. Electromagnetic radiation does not need any medium or material to travel through. It can travel through empty space. Now, there are lots of forms of electromagnetic radiation. Visible light, or what we call light, is just one of those many forms. So electromagnetic radiation, as you look at that diagram that you have, has radio waves, which have your cell phone. So if you like your cell phone, those are where radio waves come from. Also TV waves are included there. Microwaves, which might heat up your food. Visible light, which is just this small spectrum in here. So only a small spectrum of electromagnetic radiation is actually what we can see. And then that's where our Roy G. Biv scale comes from red, orange, yellow, green, blue, indigo, and violet. And then as we go further out, the opposite way, X-rays and gamma rays, more destructive, higher energy forces or waves that we have. And if we look at our wavelengths, as we move one side, our radio waves are very large, microwaves to infrared, and then we start getting very small in size as we move across. And so these are just different sizes of the waves that we have. The electromagnetic spectrum then, the entire spectrum would be including all of the different wavelengths and frequencies. Now on your chart, it only has the wavelength listed at the top. However, one other part that we're going to be looking at, frequency, is the amount of waves that we have per given moment of time or per second. And so we start on this side, has a very low frequency, and then as that number increases by magnitudes, powers of 10, we get to a very large frequency, meaning we have a lot of waves in a given moment, even though they're very small. So if we were to look at a visual of what a wave looks like, even though we can't see most of them, the wave has a couple key parts to it. So just on number 8 in your notes, just down below, what I'd like you to do is identify the crest is at the top of a wave. So we have our crests. Trough is the bottom of the wave. And then amplitude is the height from the midpoint up to the top of one of the waves. So these are a couple key parts. The crest or the peak, the trough or the valley, the bottom and the top of the wave, and the amplitude, the height from the midpoint up to the top, is going to be a few terms that you'll see throughout throughout this chapter. Our first term, lambda. Lambda is wavelength. And so this will be our first new word that we have, or new part, is going to be wavelength, represented by this Greek letter here. So this is lambda. Now lambda is going to be representing wavelength, distance between two equal points on a wave. So if we were to go from one point to another equal point on the wave, or if we started here to get to the equal point on the wave, would be one full rotation over to here. So that's going to be a distance measurement. Meters, centimeters, nanometers could be example. The way I like to remember that this is wavelength, if you were to think about just, visually putting a few lambdas together, and you put one next to the next, and if you drew another one, and drew another one, it starts to kind of look like an ocean wave coming on in. And so wave for wavelength, lambda is going to be one of those waves. And so wavelength is represented by lambda. The other term that we have for this chapter isn't the amount of waves, but how often they occur, or the number of waves that pass a given point per second. And that's represented by the Greek letter nu. Nu is the pronunciation, and it's kind of a fancy V. It's got a little bit of a tail to it there. And so nu is going to be our other term for frequency, the number of waves that pass in a given moment. And so per second, or hertz, is a common unit for this, known as waves per second. How many waves pass a point in a certain amount of time, that time being seconds. And then as we're going, waves is to be understood, so we just kind of know it as per seconds. Now you're going to see two different ways to draw this. Since it's the amount of waves per second, it'd be the number of waves per second would be our first unit. Or another notation way to draw this is seconds with a -1 power. Both of these are the same. They're known as a hertz. It's the amount of waves per second. So if we had like 652 hertz, it'd be 652 cycles per second, or waves per second, or 652 seconds with a -1. They're all known as per seconds. So that's going to be the frequency that we look at. Now, if we were to do an example here first before we get into number 8 in the notes, how many cycles occur in 1 second? So if we said we started here, and then we have a certain amount of time elapsed, what we're going to do is see how many waves pass by a given point in a second. So if we were to start and look through at 1 second's worth of time, we would have noticed that 1, 2, 3 complete cycles happened in that 1 second, or we'd have 3 cycles per second. So we could say in that case that 3 cycles happened per second. So as we're looking at number 8 in your notes, frequency versus wavelength, we can see that we have two different wavelengths, starting with one wave to the top of the next wave, one complete cycle. So with one, we've got a larger difference in our wavelength. Smaller wavelength from one to the next part, and a larger wavelength for the other one. So right away we can see a difference between the two waves. Now our next step is to see how many waves occur in that given amount of time. So if we were to look at the top and the bottom wave, as we let them go, in a certain amount of time, our top wave, we get more waves that occur in the same amount of time. On the bottom one, we have less waves that occur in a certain amount of time. And so what we're going to look at is the idea that our waves kind of have that relationship between wavelength and frequency. And what happens is that they are inverse of one another. So if we have more wavelengths, shorter wavelengths, say on the top one, less wavelengths, we actually would get more frequency. Or in the bottom, we have a longer wavelength, so a larger wavelength. Wavelength is lambda. So they occur less frequently during time. It takes longer for each one, so we have less frequency. So inversely related are ideas between waves. What do they all have in common? They travel as a wave. So all electromagnetic radiation travels as a wave. They travel at the same speed. That'll be our next thing we talk about. 3.8 times 10 to the 8th meters per second is how fast all electromagnetic radiation travels, and they don't need a medium to travel through. So as we're going, they don't need any space. They can travel through a vacuum. Now remember, the idea is that the wavelength and frequency are inversely related. If one increases, the other one decreases. If one decreases, the other one must increase, is going to be what we look at next. We'll continue here in just a minute with looking at a little bit of calculations. So I'll go ahead and start in on the next part of the video.